Good morning, everyone. In today's session, we are going to extend our analysis from the 2D particle to the 3D particle. Remember that we refer to a particle as a body that is subject to concurrent forces, forces that intersect at a single point. And we said if that happens to any body, that body cannot rotate. So the rotation cannot happen if the forces intersect at a single point. Okay? So now what if we have a real structure or body in 3D, and this body is subject to concurrent forces? Again, it's still a particle, but now it's a particle in 3D. And instead of having two equations of equilibrium, we have three equations of equilibrium. Now you will have to solve three equations in three unknowns. Today, I'm going to give you a problem that can be easily solved using that. But then I'm planning on my other channel, the channel about Math Made Easy, is to record a session about using Gauss-Jordan elimination method to solve a system of linear equations. And then I may also show you how to do it or to check your answer using a calculator, using matrices, so it will be easier for you. Now, okay, just to save time and, there is no reason to see me drawing stuff. I already prepared a problem for you. But before doing that, let's write the equations of equilibrium. Nothing new. It's the same thing. So we say particle equilibrium in 3D. Okay. So as we said, we have three equations of equilibrium. The first two are exactly identical to the first, to the 2D. So we say summation of the forces along the x equals 0, summation of the forces along the y-axis equals 0, and the summation of the forces along the z-axis equals 0. Three equations in three unknowns. Now, what we usually do, remember, is that in 3D, I can give you the location of the particle and tells you how far it is from the x, the y, and the z, and in which case you would create a unit vector along that and then multiply it by the magnitude of the force. Or I can give you the elevation or the polar angle, the azimuthal angle, and then, just the radius, so to speak. R or rho, depending on the nomenclature. Or I can give you theta x, theta y, theta z, and you know that will give you right there the identity, or I'm sorry, the unit vector. So we have three ways to give you the force. As I said, I will try to give you an easy problem so we don't have to solve the equation simultaneously, because in 3D it would be tedious. Later, I will show you an easy way, even if you are not allowed to use a calculator, how to at least make your Gauss-Jordan easier to manipulate. So, yeah, one more thing. In the previous lecture, in the particle equilibrium in 2D, we always assume that the forces are tensile. What if you have, because we had cables, and we know the cables cannot be compressed, so they have to be tension. But even if we are not sure whether the member is under tension or under compression, the universal way to do it is to assume it's tension. And you say, so what if it's compression? Well, if it's compression, you will get your answer in negative. So instead of getting the force is 100 Newton, you get negative 100. Negative meaning your direction is opposite. So it's so easy to figure out whether a member is under tension or under compression using this method. If you know for sure that it is a compression, like we will encounter that, say, in frames or trusses or some machines later in the course, then you can assume it's compression, but be careful, because if you get a positive answer, so the plus and the minus, some students have trouble with that. They think plus means tension and minus means compression. That is not correct. It's not correct. The positive and the negative means your assumption was correct or not. So if I assume compression and I get positive, it means, yes, my assumption was right. The member is under compression. If I assume compression and I thought it was, and it turns out to be tension, my answer would be in negative. So the negative here tells you the sense you used, be it going away from the particle as tension or going into the particle as compression, was incorrect. So negative means incorrect, positive means correct, not tension and compression. So that's why many people always assume tension, so that if it's positive, it's tension, if it's negative, it's compression, as they are used to think. But be careful, sometimes you may fall into this trap. So be careful, it tells you your assumption, not what the member is experiencing, okay? Here is the problem. So I'm not going to draw the free body diagram to save you time because it's already drawn. So I can, if you add arrows, that's not correct. Don't do that in a test. But I will do it to show you what I'm going to assume here. I have 3 cables and there is a load of 600 Newton supported by these 3 cables. So I know that the cables are in tension. Please, that is not correct. These are internal forces. Internal forces are hidden. You don't see them. You only see them when you cut the cable. Because in fact, there are 2 equal and opposite forces here, so they cancel each other. And that's why you don't see anything. But once I cut this, and that cable, these 3 forces are attached to this particle, so they appear. If I, for some reason, if I want to look at this particle, I will see that arrow here at D, here at B. But at A, there are only these 3 hidden arrows plus the load. But I'm saying just for simplicity. And again, I'm not going to redraw the X, Y, Z. Just as I said. So now we are going to write the 3 equations of equilibrium. Some people write the forces first in vector form and then take the X, the Y, the Z. Some people can do that on the fly. So let's do it the easy way. So each force first. So if I start with TAB, for example, tension AB equals. The force is in the XY plane, and it makes an angle of 30 degrees with the Y, not the X. So it is TAB, so the TAB as a vector, so to speak, equals TAB. So if you write it as a vector, that would be TAB times sine 30 I, because that's the X, sine 30 I, and it's a positive Y also, plus cosine 30 J Newton. If I do TAC, TAC is along the negative X, so it's just negative TACI, right? And finally, TAD, notice TAD makes 2 units. So this point is 0, 0, 0. So the coordinates of D are just the vector AD, right? So you're going 1 along the X, negative 2 along the Y, and positive 2 along the Z. 1, negative 2, 2. I'm going to show you a trick that we usually use if we want to end up making the problem easy and the numbers integer. Take 2 consecutive numbers, not necessarily, the sign is irrelevant, so I can say negative 1 and 2. So if the absolute value of 2 numbers are 1 and 2, right? 1 and 2, two consecutive numbers. Multiply them together, you get 2. If you use these 3 digits, then the length of this vector is 3, one more than the product. Meaning if I take 2, 3, again, I can make it -2, -3, -2, +3, +2, -3, it doesn't matter. But if I take 2 and 3, and their product is 6, if I use those as my position vector, 2, 3, 6, then the length of that vector would be 7, one more than the product. That's always going to be the case. 3, 4, 12, 13, 4, 5, 20, 21, and so on and so forth. That's a math property. So I know that the length is 3, right? So I can say it's TAD times 1/3 I minus 2/3 J plus 2/3 K. Of course, you can say that AD as a magnitude equals the square root of 1 square plus -2 square plus 2 square equals square root of 1 plus 4 plus 4 equals root of 9 equals 3. So we know that. So the unit vector is 1/3, -2/3, 2/3. And finally, my force F is -600 K. It's going down along the Z, so it's -600 K. Now I can write my 3 equations of equilibrium. I can say summation of the force along the X equals 0. Sine 30 is 1/2, so 1/2 TAB. Plus minus TAC plus 1/3 TAD equals 0. The second equation, summation of the forces along the Y equals 0. √3/2 TAB. There is nothing for TAC, minus 2/3 TAD equals 0. And finally, my third equation, summation of the forces in the Z equals 0. I don't have a K, I don't have a K, I only had. See why I made it easy for you. 2/3 TAD minus 600 equals 0, so it's easier to write it equals 600 Newton. Now, this is equation 1, equation 2, equation 3. So now solving equation 3, right? So from equation 3, we get 2/3 TAD equals 600. So you're going to multiply that by 3/2. And you get TAD, 6/2 is 3 times 3 is 9. So you get 900 Newton. It's an easy one. So the tension in this cable is 900 Newton. Once I know that, I can take, this would be -900, right? Because if that's 900, the negative of that is -900. So we can say from 2, you get √3/2 TAB. You can use the calculator. Oh, let's write it first. So √3, and when I move this to the other side, it becomes positive, so equals 900, right? We already found that 2/3 TAD, which is this guy, is 900. So this minus 900 equals 0. You add 900 to both sides, so you get that. From here, TAB would be 900 times 2 over square root of 3, and you get, wait a second. Is that correct? Seems like it is. Just a second. In the Y. Why don't I see that in the Y? Yeah, TAB is correct. Root 3 over 2 minus 2/3. And this one doesn't have, this one doesn't have. Okay, so it should be. Oh, I'm sorry. I used TAD, and this is 2/3 TAD, right? So that should be times 2/3 or 600. TAD is 900, but 2/3 TAD is only 600. So either I write 600 instead of 900. I thought it couldn't be that high. So I'm sorry, it's my mistake. I should have used 600, not 900 here. So I could have said, since TAD is 900, 2/3 TAD is 600. So root 3 over 2 TAB minus 600 equals 0, or root 3 TAB over 2 equals 600, not 900. If I want to write 900, then that would be TAD, then I multiply it by 2/3. So very sorry. So that should be 600 times 2 over square root of 3, and you get 692.8. 693 Newton is good enough. And finally, from 1, we solve for TAB. So we say 1/2 TAB minus TAC, which is oops, this is TAB, so we are solving for TAC. 1/2 TAB, which is 693, minus TAC, plus 1/3 TAD, which is 900, equals 0. So when I move this to the other side, I get TAC equals 300 plus half of that. So I divide this by 2 and add 300. So I get 646.4, 646 Newton. Again, sorry guys, I didn't see the 2/3 here. So TAB, TAD, so let's write this TAD, and TAC. So as I said, this was an easy 3 equations that can be solved, one at a time. In many other problems, you will see that that's not a nice number like a 3. It's like root 59 or whatever. So in that case, what do we do? I may have a special session to show you how to solve problems that are where the numbers are more complicated using Gauss-Jordan elimination method. I promise you, I said I'm going to have a session on solving linear equations, especially 3 by 3, because that's mostly what you will encounter in a statics course. 3 equations and 3 unknowns using Gauss-Jordan elimination method in my other channel, which is Math Made Easy. Thank you very much for your time, and hope you have a great day. See you soon. Bye.